caught up with the homework that I wanted to give, so, or nearly, so I'll have the homework up by the weekend. So, from where we were, I wanted to put together the boson path integral and the fermion path integral, just so we know what the full structure of the path integral is, and just do the Yukawa theory in path integrals. And so there's no surprise. I'm just pointing out that there's no surprise. E to the I, the connected diagrams with sources for fermions, and say a real scalar is equal to the Grassmann path integral for the fermions, and the usual C number path integral for the scalars. And the action for Yukawa theory plus the source for the scalars, integral d4x. Source term for the scalars plus sources for the fermion. Okay, and the action is equal to, say, take the case that the scalar is parity odd. Like that. That was a slightly neater version of it, remember? You could have some lambda 5 to the 4th if you want. Anyway, you get to choose whatever action you want. At the moment, we don't have any filter for choice of actions as long as they're relativistically invariant. But the source terms sit here, and functional derivatives with respect to, so delta, delta, eta, delta, delta, eta bar at some x and y, and say delta, delta j at some particular z of w will be the time-ordered product of psi bar of x, psi of y, phi of z, and you can provide the values of I. But it'll automatically be that. And in perturbation theory, you'll get all the usual Feynman rules, again, basically because we've made sure that we've got the Wick theorem for the fermions and the scalars. And in free field theory, they don't talk to each other, so there's no other correlator. So the interacting theory, we have interactions, but we just Taylor expand in the small coupling to whatever order of perturbation theory we want. Then it's Wick's theorem in free field theory, and we get the usual Feynman rules. Okay, so this is it. Other than gauge theory, we have sort of a typical theory of fermions and bosons. In path integral form, it's very tidy, it looks very relativistic. It's not obvious that probability is conserved, that there's a unitary S matrix, say. but it's equivalent to the Hamiltonian formulation, as we've proven. And so, in perturbation theory at least, we're done. It's all good. Okay. And again, I've written it, it's a kind of mnemonic in the sense that the epsilon terms needed for propagators are implicit in what I've written here. But we could, as we did before, we could try to write that out more carefully. We can write that out. Okay, so that is it for path integrals, at least pre-gauge theory. I now want to start using path integrals as a slick method for approaching, approaching the construction of what's called the effective action. Which is another function of phi, like the action itself, or more generally. And the general approach to renormalization. Okay, so that's broadly where we're headed. So we're trying to make everything as efficient as possible, to have everything in terms of generating functionals, so that we can treat all diagrams in one shot. So then we just have to be sophisticated about our use of subsuming all diagrammatics, diagram by diagram, into functionals, these generating functionals. In order to do that, I need to start with the subtopic, which is what was called the loop counting parameter. Okay, and so let's first do a simple example where, so generally we think loop diagrams are a multi-loop diagram is a very high order calculation of some process, some Green's function, an S matrix element, whatever it is. But by working to 10 loops, you're doing it very precisely. At least if the coupling constant is small, then it's getting you rather high precision. So it seems like the coupling is sort of, if you work to high order, you do more loops. So in some sense, they're correlated. So we want to make that official, but also try to link it to this other thing that we think of as the parameter that controls quantum mechanics, namely Planck's constant, which up till now has been set to 1. And so we're trying to relate the two. Okay? So that's what this thing does, and it'll be very useful in this discussion that we're going to have about the effective action and renormalization. So let's see. Let's find the fourth field theory. The action is interval d4 x. We already see a sort of tension between the two ways of thinking about quantum corrections as loop corrections. Okay? On the one hand, we think that the coupling constant is what controls higher order loops, more powers of this. And on the other hand, sitting inside a path integral, we have another way of thinking of the classical limit. Okay. First of all, by dimensional analysis, path integral knows about the classical action only in the form e to the is. But by dimensional analysis, it must be e to the is over h bar, because h bar has the units of action. Okay. So this previously set to 1 thing is sitting there. So somehow we think of h bar as the thing that controls quantum corrections, which we often think of as loop corrections. And it sits there, whereas by Feynman diagram analysis, we know that every extra loop that you do is controlled by this parameter lambda, and they are sitting in different parts of the action, and so it's not obvious in what sense one is related to the other, but there's a very simple way to see that in fact they are one and the same thing, okay? And that is, so let me get rid of this then, and just analyze the action, and say, no. This is equal to this, more correctly. So we're going to rescale phi. I'm going to try and do a field, I'm going to try and change the integration variable, which is always I'm allowed to do. I'm allowed to change my integration variable. I'm going to try and change the integration variable so that the lambda shows up in the same place as the h bar. Then I will say, no, there's not 2 ways to think about quantum corrections. There's only 1 way to think about quantum corrections. So, if you stare at this, you'll invent it for yourself. I'm inventing it right now. Phi goes to phi over square root of lambda. Okay? Then this will go to is it lambda? That makes no sense. Wait, it must be square. And what did I do wrong? That works. No, it's all good. It's all good. Okay. So we've completely got rid of the lambda in the action and put it all there right next to the h bar. And we did it by just a field redefinition. I mean, which, if you think of this as a glorified integral, is just by rescaling the integration variable, which means there's some Jacobian for doing it. If you think of this as a glorified integral, then you rescale the integration variable, there's some Jacobian, but it's a, so again, let's, so there. I don't care about proportionality constants that are not J-dependent. They cancel out when I'm calculating connected correlators, namely the log of the partition function, if you like. So you can write it in this form, and it says that, again, if you can calculate the new J-dependence, you can easily supply the old J-dependence. That's trivial. And this is just the efficiency of the source, which is an input from the outside anyway. Okay. So we end up with this, and you can see that it really is h bar and coupling are the same thing. In other words, it wasn't wrong of us at the beginning of relativistic particle physics, when we were learning it, to set h bar to 1. And then to go and say, well, h bar is small, and that's why quantum mechanics has small quantum corrections. It's there because the coupling constant is small. Okay? And in fact, whether you think of h bar as big or small, since it's a dimensional quantity, if in the original way of thinking of h bar, that's meaningless. Okay, to say whether it's big or small. But you see, what gives it meaning to say whether h bar is big or small? It's a code word. To say h bar is big or small is a code word for asking whether this coupling constant is big or small. And so, in perturbation theory, we'd like to say lambda is small. We hope it is, and that's precisely the sense in which you can say h bar was small. But we, normally in this class, are saying it correctly. H bar is 1. That's silly to talk about h bar at all. The coupling is small, but it sits in the same place in the path integral that h bar would sit by dimensional analysis. Okay, so that's a quick way to remember. Where is that coupling? Well, it's there secretly in this way. And this way of writing it is some holdover from, in this way of thinking, you'd say this is some holdover from, again, some past conventions. For example, you'll notice that this is nothing but a wave, what I called before, a wave function renormalization, right? I'm renormalizing the scale of the field. And in particular, if you look at the kinetic term, it looks canonical, but it's not. That lambda has to be multiplied, so 1 over lambda times that. This is not the canonically normalized scalar field. Okay. But it is some normalization of the scalar field in which the coupling constant is homogeneously out the front of the action. So this is a very useful way of saying that. So in any process, any diagram even, or any process, can be dressed with extra loops, each suppressed by I'm going to say therefore, I'll explain why, by lambda h bar. So look at some correlator that I'm calculating. You can say process, or you can even say correlator. It could be S matrix, but let's just do this on some general thing in this language with J's attached at the end in the usual sense. I'm going to fix, I'm doing a 10-point correlator. I'm doing a 5-point correlator. I've fixed the number of J's. So whatever the sort of change in the normalization of J by some root lambda to the 5th power or something, it's fixed. I'm fixing 5 points. All I'm considering is whether I'm planning to add a couple of extra loops. So for example, here I've now added 2 extra loops by doing this. Relative to whatever I had before, I can add some number of extra loops. Here I've added 1 extra loop. And you'll see I had to use 1 power of lambda to do it. Here I've added 2 extra loops. That one and that one. And it's cost me 2 powers of lambda to do it. Okay? In these connected diagrams. So, in fact, we are seeing by the example I'm doing that indeed every extra loop comes with a lambda, but by this argument, since lambda always, it's only here in this calculation in that it's multiplied by h bar, hence it comes with h bars. And if you were really putting in the h bars and going back to standard person units, it would be with those h bars. They're controlling the loop expansion together. You might say, wait a second, no, I see a lambda. No. This lambda goes away because it only gives rise to a Jacobian proportionality constant, which is not relevant for calculating the correlators in W. Okay. This, however, there's a root lambda to the fifth, but it's an overall root lambda to the fifth. Okay? It's the relative thing between whether I decided to draw this or not is fixed. Okay. So this is a true statement. And each extra loop is suppressed by an extra lambda h bar. Okay. When you say h bar is small, it's really just a kind of code between you and me that the coupling constant is small. Now, the puzzle seems to be, would then appear to be that if I had a theory with more than one coupling, how do I have more than one h bar, right? And so let me just do the next simplest example, and then I think you will be able to think of how to say it generally yourself. I won't waste the time doing it. Why we have it right here. Look at this theory. Two couplings. How can they both be h bar? Okay. So of course there is that h bar there. So in a sense, what we're looking to do is to put the couplings, 1 over the couplings out the front of the action. And so instead, what we do is we write G is G bar times C. I'm introducing a new parametrization of the coupling. Seems a bit redundant. And then I'm writing the scalar coupling as lambda bar C squared. And I'm going to take, of course, I insist that we're doing perturbation theory in this course. So G and lambda are smaller than 1, parametrically smaller than 1. But I'm going to take G bar and lambda bar to be parametrically order 1. If you want them to be small, all the better. But you can take them to be order 1. But I'm taking C to be parametrically small compared to 1. In other words, it's C that puts the small coupling into G and lambda. It's not the G bar and lambda bar. That just differentiates them by some order 1 amount. Why did I make this C and this C squared? Because I know the answer, but you'll see the systematics for yourself, I hope, in a second. So let's just do this transformation. And of course, you can redo the sources. The sources can be trivially scaled to keep the source term invariant. That, I hope, is obvious. I won't bother to write it out. So what do you get? You'll get, so this will work the same magic. You'll have 1 over, if you want, let me put the h bar back. That's 1, so who cares? And C squared. And then, yes. Oh, this was of course integral. It's integral. And then you'll have this d mu phi squared minus m squared plus 2. Okay, so what you end up with is an action where all the couplings are order 1. In other words, you're not getting your perturbation theory from here, and hence you're not getting your loop expansion because of these G bars or lambda bars. They're just a way of sort of differentiating in an order 1 way, this from this, in terms of its strength. You're getting it from the C. Okay. And every extra loop in contributions to some fixed correlator costs or suppressed by C squared H bar. And so you see that's the way we get through the multiple couplings. But let's just check what I'm referring to. So for example, here, here's a 4-point scalar correlator contribution. It's tree level. Let's compare it with, say, this one, which is 2 extra loops, and it goes like lambda squared. So it's lambda bar, so it implies an extra lambda bar squared c to the 4th, and of course therefore h bar squared. So yes, it's suppressed. If you want to say it's parametrically in other words, to me it's only of incidental interest that in detail there's a lambda bar squared here. I'm thinking of that as some order 1 thing. But the suppression, formal suppression, is the 2-loop factor c to the 4th h bar squared, following that rule. Okay. There is another thing you could have done, for example. Here's another contribution to the same thing. And this one implies it implies that you don't, so that one had a lambda already, if you like, right? Here, I don't. So this was a lambda. If you want, it's lambda bar c squared, right? This thing goes like y bar to the 4th c to the 4th, which I can always write as my original answer, so if you want, which implies an extra y bar to the 4th over lambda bar c squared. So relative to the thing, the tree level contribution, it is order c squared, and hence h bar c squared. But there's some order 1 ratio of these order 1 couplings there, but I'm just pointing out that every loop comes with extra powers of h bar. This was important, yeah.
So when you write your couplings like g, c, and lambda c squared, your g is suppressed, or your lambda is being suppressed by a power of c relative to g, right?
Yeah.
So that's not entirely, like you're saying something
it seems
about
slightly.
the order. No, you're definitely saying something about the order of the couplings. G and lambda, the original ones, right?
Indeed.
Okay.
Now, suppose you actually wanted to, as I said, there's absolutely no harm done by having a G bar and a lambda bar. Sorry, there's nothing wrong by one of these being even smaller than order 1. It doesn't bother me. I just don't want to have them be big and undercut. In other words, when I point to something as let me say it like this. If you wanted to say, I want to think of a theory in which G is equal to lambda, and they're equal to 10 to the minus 3. I want that right. Then I would say, if you want to think of that one, then think of G as equal to, say, so let me take G bar is equal to, say, 1, and no, I'm going to take lambda bar is equal to 1, and g bar, can I make it 10 to the minus 4? So I have to square root the scope. And g bar is equal to 10 to the minus 2, and c is equal to 10 to the minus 2. So, you see, I can have them both be small, as long, and even comparable in size. It just means taking one of the things that I said was order 1, but what I meant was not bigger than order 1, and having it be even smaller than order 1. So, what you're doing in all of these things is pulling out sort of the maximally, I don't know, the minimally small factor in this. But there's actually a general rule for which I'm going to just leave it as an obvious exercise, but so I'll tell you the answer and then play around with it. Why was that c and that c squared? If it's a 3-point coupling, make it c. If it's a 4-point coupling, make it c squared. If it's a 17-point coupling, like 5 to the 17, make it c to the 15. So just make it c to the number of fields in here minus 1. So you're not going to need that a lot, but yeah, this generalizes in that simple way, and you'll see that's. So just play around with the graphology of this, and we'll see that that's the rule that makes every loop come with an extra power of c squared h bar. And but yes, you can think of both of them as small and equal by deviating from order 1, but I don't want you to make one. I don't want you to make anything bigger than 1. That's all. Okay, so. On that. This identification of the coupling with the h bar is very useful in. I wish I had sort of done it first, but I didn't. Is very useful in just the sort of quantum mechanics version of the classical limit and the semi-classical approximation. Okay. So as undergrads, you learn, you start from the classical limit, you quantize the theory, then try and see under what situation you end up back in a kind of classical approximation. You can do WKB and various other semi-classical methods. In the path integral, there's sort of a uniform way of seeing why something would ever be classical, even though you're doing path integrals. Okay? And the idea is simple. I'll just say it in the case of field theory. So you have something, again, I'll just do scalars. And so the naive rule would have been what happens as h bar goes to 0? So let's think, again, like people who didn't know that h bar is 1. We think of it as somehow appropriately small. Okay? So if h bar goes to 0, then you would say, look, as I vary, this could be quantum mechanics or quantum field theory, as I vary my field a little bit, as I start doing this integral and I start varying from one field configuration to another field configuration, the action changes. I mean, this full action changes, okay, including this one. The full action changes by some amount. But h bar is so tiny that I'm starting to suffer from wild phases. That is a small change in the configuration, but a really small h bar. This phase can suddenly turn 180 degrees the other way, and I'll get a lot of destructive interference. And this thing only gets more and more the smaller h bar. Okay. So with the state, so where does that fail? Where's the dominant contribution going to come from? It's going to come from configurations where when you change the phi a little bit, this source plus action doesn't change, or changes very little. Okay. In other words, where the variation of this action is equal to 0. Okay, that'll be the dominant place that you would get it. So the stationary phase, so that's where the stationary phase approximation comes in. Which we appealed to, for example, when we were doing the long-time asymptotics of Green's function, of the free particle Green's function. And so we'd say that it, in fact, goes like e to the I over h bar s of phi plus j of phi, it's j phi. But where I'm no longer integrating over all possibilities, I'm actually dominated by the phi where this action is stationary. So such that delta s delta phi plus j equals 0. If you want, we can say this phi is dependent on j in the sense that phi j solves this classical equation of motion for the action with a source term. Okay, so the Feynman path integral, the principle of geometric optics coming out of as approximation to wave optics, all comes from this basic thing. Okay, if you want geometric optics coming out of wave optics, going through Huygens principle, which is like path integrals. That's all we're doing. We're recycling it in this very high-tech language, but it is precisely that, to say this is the geometric optics approximation to this Huygens principle way of doing wave optics. That's the sense in which formally, so it's formally true that as h bar goes to 0, this path integral is living in this way. But now we actually understand what we mean by that. What we really meant by that was that h bar is 1. You can't say that. We know it is insane to say that it goes to 0. What we're really saying is that this h bar for parametrically small lambda, and by the way, this is the absolutely leading thing. The beauty of the path integral is then you can ask, what's the correction to this leading statement? And what's the correction to that? And so on and so on. Okay. But let's just go with this leading thing, because we have other ways of getting the subleading things. That we're saying this is the absolutely leading thing, the leading contribution to the connected diagrams is given by this. Leading in what? Leading for small lambda. Okay. So therefore, e to the I w, now look at this brilliant observation relating the diagrammatic approach to the generating functional approach, which is where we make contact with the high-tech methods. So therefore, so we already have a name for the leading thing for small lambda that contributes to the connected Green's functions. It's called the tree approximation, because we know that loops cost extra powers of couplings. Okay? So the tree approximation is already the name of the contributions to, that dominate for lambda goes to 0. But now we're seeing that the stationary phase approximation is also, the leading stationary phase approximation, is also got to be the same thing. There's only one leading thing in lambda, okay? Where the phi sub j I've defined is the thing. So that's what it says. In fact, I can just take the log of both. So, having used the h bar as a kind of reminder of old-fashioned ways of thinking of quantum mechanics, I can set it to 1 and just read this thing here. And in fact, I can therefore just cross off, I can take the log and just say this. In fact, there's no proportionality. This is now. Let's write this. The proportionality would just say constant, irrelevant constant. It's like a 0-point energy or something like that. You would toss it out. You don't care. So this is the result, right? No, this is correct. Okay. Anything more I want to say about that? Yes. When we solve this, we have to provide. So, look at even free field. Look at even free field theory. We're going to get something like box minus m squared phi, right? The variation of the free action, plus j equals 0. But you recognize that equations like this require some sort of boundary condition to decide how to solve the wave equation. And so with this example, with the I epsilon prescription. Okay. If I had some interactions, I would have something that looked like plus lambda phi cubed. Okay. I can solve this in perturbation theory, but I need to know the zeroth order solution. That's the I epsilon prescription. So there is an I epsilon hidden in this statement that we've gone through, and it's hidden in how you decide to solve this. Okay. Question?
So, in elementary quantum mechanics, when the classical limit is used, there's no corresponding lambda parameter. And this is more just...
Sorry, say that again. In elementary quantum mechanics.
Well, so we started off and we're calling this the classical limit,
yeah,
because it's formally like the classical limit that you do in elementary quantum mechanics when
yes,
you take h bar to 0.
Yeah.
But it's behind the formalism. It seems it's very different in that here we're showing that it's equivalent to lambda going to 0. Whereas I guess in quantum mechanics you're saying the action is given to infinity.
It's not really the old quantum mechanics were dumb and they should have chosen h bar. So you'll notice that. So you see, it's what connects to experiments and what got named first. And you'll remember, you'll remember that when we did the analog of quantum mechanics and quantum field theory, that we saw that in some sense the field theory side was like, so this idea of 5⁴ plus was vaguely analogous to now, here's the typical problem you see in quantum mechanics. You would say, I'm doing a harmonic oscillator, but it's not. It's an anharmonic oscillator. Okay? And then we can do some perturbation theory for transitions and blah, blah, blah. Okay? It's just like an atom. No big deal. But you haven't got an exact solution. You just solve that problem. The analog here is phi is like x, and the omega sub p here is like the omega, if you recall. Okay. Indeed, we say, look, there's an h bar, and it means something. I know I go out and measure it, and so on and so on. And that's because one of the things in this that I told was sort of confusing before is that this mass, m, is like the wave function or normalization of this guy, which we normally take to be 1. Okay. But the trick for putting it in this ultra slick form where the lambda is there is by doing wave function normalization. However, if I peg you and say, you know, you have to talk, well, I have to talk to experimentalists. And they insist that half mv squared is the formula that the rest of the world, the engineers, all talk about. And so we have to stick to this way of talking about x. Then that pegs me here. I can't do that move. Okay. But indeed, the logic of this is absolutely right. It really has got the truth to it. And think about it this way. If I keep h bar the same in, say, hydrogen atom physics, and I take the masses, so the way you should think about it is the hydrogen atom very quantum mechanical? And the answer is, that's a silly question. You see, the inner orbits are highly quantum mechanical, whereas the outer orbits obey Bohr's correspondence principle. So you can start to see how classical mechanics is a good approximation to those outer orbits. But the inner orbit's totally quantum mechanical. That's why quantum mechanics was invented. But now, let's suppose that I am in one of those inner orbits, and I suddenly switch the mass of the electron to the mass of the muon, okay? Which is like doing one of these dreadful field redefinitions. So suddenly you can ask, well, is that sort of, it's some superposition, because when you do sudden switches, you get some superposition of states. But is the sort of basic thing that you created, that orbit size, is that very classical now, or very quantum mechanical? H bar, of course, hasn't changed at all, right? But in fact, you know that the Bohr radius depends like 1 over m. And so, when you've taken this inner orbit of the electron-hydrogen atom, and you make the electron a muon, that turns out to be one of the outer orbits of the muon theory. You see? The inner orbit of the muon theory would be at 1 over m mu, or alpha squared, alpha over m, alpha, 1 over alpha m mu, okay? So suddenly this thing feels pretty, it feels like, other than there's some superposition of things, but you can decompose it into a set of sort of classical looking orbits for the muonic hydrogen, which is to tell you that actually the mass, for whatever other things are being kept fixed, that mass is actually controlling the h bar. And you can see there really is sort of this wave function normalization trick that puts, that connects all the different bits. So the quick answer is the charge of the electron, the mass of the electron, and h bar are tied together in terms of what you see. And of course, what orbit or what rough ballpark of you're probing the system. And the words h bar is small, or h bar goes to 0, is just as slick and too quick a statement in standard quantum mechanics as it is here. We're not actually doing anything worse or illegal. Actually, this is the truth. And it's just as true in the hydrogen atom. But the hydrogen atom, you are not used to thinking about how sensitive I am to the mass of the electron and the size of the orbit, and taking those ratios into account. So it's a little less relativistic, and you have to think it through. You can do it by just, instead of the hydrogen atom, I could think of a harmonic oscillator as just as good. And you should, if you want, look at this exercise of just thinking these things through and see whether it correctly does everything you want. But there's nothing strange that's happened between quantum mechanics and quantum field theory. It's just that for the first time we're bothering to try and understand these quick words. H bar is small. H bar is small if you're people made out of a certain M. and certain sizes, and so on and so on.
No, sorry.
Okay. So look, this is a beautiful functional way. Notice it's, in fact, this is a, oh, I should have put integral b4x, of course, right? Integral. This is a, this looks like a Legendre transform. And in fact it is. It's just that it's a functional. Okay? It's the relationship between Hamiltonian and Lagrangian. Except then here you'd be integrating, you know, the everything, the variables here would be functions of time. Here they're not functions of just time, they're functions of time and space. Okay? But other than that, it's a Legendre transform. But this thing that we can see graphically with our eyes, tree structure, tree diagrams, turns out to be something that you can say functionally by being blind to any tree-like structure, and just say, oh, it's the thing you get from the classical action by doing this Legendre transform. And in the Legendre transform, you have to know how to get the J, how to get one variable. You know, the heart of it is treat this guy as the independent variable and think of this guy as the dependent variable. First, have we done that? Yes. Because I'm telling you, that's in fact the notation I used makes that clear. Phi j takes this independent variable and you find this phi j as a consequence of that, in fact as a functional of j, by solving this equation. It may be very hard to solve, but whatever the solution is all the tree diagrams in one shot, by just solving this equation once, but keeping that I epsilon prescription in mind. Okay? To tell you about what things, again, the reason you're doing that is because you can always add a homogeneous solution to any solution to this, and you get another solution, and you're trying to break that degeneracy. You need some boundary condition. That's what this I epsilon is. Okay. So, because of this, we sometimes say, we sometimes say this is that the tree approximation is the classical approximation. We sometimes say that. And hopefully it's clear why, because it looks like you're solving the classical equations of motion. This is the thing that puts the quotes. Because I'm telling you to solve it with the I epsilon prescription, which, if you go around reading, say, Jackson, another beautiful classical field theory book, or Misner, Thorne, and Wheeler, another great classical field theory book on general relativity, you don't keep talking about the I epsilon prescription. So there, if you're doing perturbation theory at all, you'd be using some sort of retarded Green's functions, which would be a different, in fact, go back to your Peskin chapter 1 or something, you'll go through all the different possible Green's functions, and that would be a different prescription for solving this equation perturbatively. So I still insist on the quotes, okay? But I'm saying it, in fact, I wouldn't bother to say it at all, except this is going to makes contact with other ways that you'll hear the tree approximation described as a kind of classical approximation, or the semi-classical approximation, and so on. But other than this mild little thing, physically it's super important. Tree-level quantum particles hitting each other do not look, walk, or talk to an experimentalist like classical waves. That's how much is hidden inside this I epsilon prescription. However, mathematically, we don't fret, this doesn't cost us so much agony. Mathematically, there's a clear analogy. That's it. And indeed, if you have tree-level processes involving many bosons in a kind of coherent state, then you will actually get the classical limit with the usual classical retarded propagators. But that'll be an approximation. This is a different approximation. That's an approximation for sort of many quanta, and this is an approximation for a few quanta, a few particles, with weak coupling. Okay, so looks like this. Okay, so then to really say it's a full functional Legendre transform, we'd like to see that there's the inverse Legendre transform relationship as well. Okay, so let's just do that, and then we'll have nailed it. Good. Inverse. Okay. So to get that, first note that so let me make it as easy as possible. Delta delta J of the top equation there says that is equal to and taking delta delta J at some point x, say, is I pulls it down an I phi x like that, and so if I put minus I there, then I get that, and therefore delta W delta J. So if I just divide, if I take this line and I divide by the partition function itself, I get delta W delta J is equal to, and you see this thing, once I divide by the partition function, the path integral again, is nothing but the vacuum expectation value the J means that if you really force me to write it out, it's time of e to the minus I integral dt prime phi Heisenberg of this, and this is what do I really need? Yes. I could write this out. All I'm saying is I'm calculating phi. The reason this is at all subtle is J is making the Hamiltonian time dependent. And so when I say who this, if I want to name this, if I could just set J equal to 0 after doing the derivative, which is the way I normally tell you to think, use J, derivatives with respect to J, to pull down whatever time ordered product you want to calculate, and then set J to 0 because you're done with it, out it goes. But we are trying to keep J non-zero so that we can take all the derivatives with respect to it after we have done a whole bunch of manipulations, okay? So I don't want to take it to 0. But then naming this guy, like what is this that I've calculated in Hamiltonian language, well, I'm doing it, but I realize I have absolutely no need for it. So I will stick to pathetical language here. Excuse me while I erase this nightmare. I'll just try and write it down myself.
Can you just think of it as the vacuum in the presence of J?
You see, if J was a constant in time, it would just be the so there'd be a new vacuum, right? And then it would just be the expectation of phi in the J vacuum. And that's intuitively all that it is, except J is a function of time. So the notion, so you don't even have energy eigenstates. So you can't even say that something's a vacuum. Now, of course, if J is only turned on for a finite period of time, eventually you go back to having the standard Hamiltonian, which is time independent, and you have the vacuum. So what it really is vacuum, a Dyson series or a time-ordered product of e to the I j phi, all the way down to the time x naught. Then you have this operator. Then you have another such exponential, and then the vacuum. Now, I was planning to write that out, but I don't need it. I don't need it. I mean, I can say in pathetical, what is this in quantum mechanics? Well, it's this. It's this thing here. It's whatever this thing means, okay? Because you could ask me just there too. Fine, you wrote it all down. What does it mean? And I know, but I mean, it's not a classic object. It's a mess. But the meaning it has here is when I decide to do the truth. So here. So let me write this first. Let's do the obvious thing. Let's write this side.